Okay, so I'll be talking on inductors and some microwave passive devices. It's not the same as you use in analog circuits like resistance and capacitance, but I think all of you have already studied inductors in your courses, but not microwave as such. So looking at this structure of the inductor, this is the normal structure, metal wire wound up around a solenoid or a core which is soft iron or maybe something else, and the inductance actually depends on the magnetic field in between the wire which you encircle around that bar. Now this is quite different from what we have in CMOS. The right figure shows what we have in CMOS, because CMOS is a planar structure, you cannot just wind around wires around a simple solenoid. So this is actually a metal layer structure and it is wound around in the shape of turns, and these are the two metal terminals. Now what is the important point of difference between these two structures is that, see, the important point about inductors, I hope you know, is that the inductance is proportional to the rate of change of magnetic field. Okay, so which one do you think will have a higher magnetic field, the CMOS one or the original solenoid one? Yes, the solenoid one always has a higher magnetic field, hence the inductance value will always be higher in this case. However, also another point is that any inductance, as Ashudev already mentioned, any passive as such is always associated with a parallel capacitance, also maybe a series resistance. Now, what does this capacitance actually determine? At a lower frequency, this will behave as an inductance. Okay, so if I plot the imaginary part of the input impedance, looking from this point, initially it will be a linear because of the inductance. Then after the resonance frequency, which is this, will become negative because of the capacitance, and this will go up, okay, with frequency. So the inductance value can directly be found out from the lowest point of the curve and take the slope of this curve, that will give you the inductance, and the capacitance as expected will be obtained from the highest point of the curve where we get the capacitance. Now the difference between the solenoid inductance, say the metal bar structure, and the CMOS planar inductance is that this inductance has a much higher capacitance because it has a much larger surface area. So below you have much larger capacitance. Hence, as expected, the resonant frequency, as it depends inversely proportional to the capacitance, that will decrease in case of CMOS, which severely limits the range of frequencies we can use inductors. Okay. Another point is that you all know that when a conductor conducts current, there are eddy currents induced in nearby conductors due to magnetic fields. So suppose the main losses of CMOS comes from the eddy currents of the substrate. Now due to currents flowing in these layers, on the top metal layer, there are eddy currents introduced below the substrate, in the substrate. That severely limits the losses, limits the quality factor of the inductance. So these are the main three disadvantages of CMOS inductors. However, it's a much cheap process than to wind coils around a solenoid. Now this shows the whatever curve I mentioned here. Now another way to characterize an inductance, say I include a series resistance also. So RS, and this is L and C. Now another way to characterize an inductance, the quality of the inductance, is, as I mentioned, the quality factor. Now for an inductance, we all know that it's omega L by RS. This RS contributes the loss of the inductor. So the lower the RS, the higher the quality factor. Now this curve actually shows the variation of quality factor with frequency, and after the self resonant frequency, this definition does not apply, and hence if we continue using this definition, the quality factor will become negative because it's capacitive, the imaginary part becomes negative. So that's what we see from the curve here. Now this is the actual structure what I was talking about in 3D, showing the substrate, and above that there is a metal layer structure. Suppose CMOS has different metal layers, so any one metal layer could be used as the inductor top layer, but in general we use the topmost metal layer as the this metal layer because it is the thickest. So the more thick, the less the losses, the less the RS, the series resistance. Also note here that there are several parasitic resistances and capacitance associated with this inductor, mainly the substrate resistance and the AP resistance, because we generally make devices on a separate very good quality AP layer, AP silicon layer. Now that also contributes to AP resistance, which is less of course. We also have the oxide capacitance. This is the dielectric oxide. Okay, see the CMOS metal layer structure is, this is the topmost metal layer. You can either connect by vias to the bottom layer structures. Say there are say 6 metal layers in a 0.18 micron CMOS process. So we are using the top metal layer to fabricate this type of structure. Okay, but in between there are silicon dioxide. This acts as a dielectric, and this acts also as a capacitance. So this capacitance is mainly of the mainly determines the self resonant frequency. Also there are additional fringe capacitances, because the current flows through this in this path in a spiral, and between these paths there are also fringe capacitances. So both these factors contribute to the CP. So this is the model of a RF model of an inductor. It's called a 9 parameter model because it has 9 parameters. The series resistance, the inductance, the capacitance parallel, and also the parasitics of the oxide as well as the substrates. Okay. Now the problem with fabricating such a square inductor comes from the technology point of view, because you know we use photolithography to etch out parts of the oxide, or to get the masks where to do the metallization. Now that is very difficult to, it's very difficult to get exactly a square portion. I mean, this edge matters, as Ashu have already told that we often do this, cut the line so that we don't get an edge. So there are various structures to the inductor depending on that. See, for example, this is the square inductor, and this is the, go to the slides. This is the polygonal inductor. We have wound it out in the shape of a polygon. Also, we have ideally would have been a circular inductor that would have the highest magnetic flux density and the highest inductance. However, exactly getting a circular is also impossible. So we stick with polygonal structures, and these are the typical dimensions. The edge to edge distance, inductance is defined by this edge to edge distance, the width of the metal strip we are using, the separation between the two metal strips, and the total area. Now as I already mentioned, the more the total area, the more the capacitance, and the less the self resonant frequency. Now let us take a normal planar square shaped inductor. Okay, and try to see what determines the inductance and the quality factor and the resonant frequency. Now suppose this dimension, let us name it as D. Now if we, what will happen if we increase D, keeping the same number of terms, everything the same, what will happen to the magnetic field? Yes, that means the inductance also increases. So the more the D, the more the inductance. However, since we have a larger area for the current to flow, we will have more substrate losses as well as more capacitance. So as D increases, F resonant frequency decreases and quality factor also decreases. Another factor is the width of the metal line. Say, let's take it as W. Now what will happen if I increase W? Yes, the series resistance will decrease, less loss, so the quality factor will increase. And what will happen to the capacitance? We are making the line wider. Yes, the capacitance will increase, and hence will also have a less self resonant frequency. Okay. Another thing is that the spacing between the two metal lines, name it as S. Now think analytically what will happen about what will happen to the magnetic field if I increase S. Say magnetic field in between these two metal lines. Note the direction of the current. This is the direction of the current. So through this line the current flows here, then it comes back, again flows to the same direction here. So if I increase the separation between them, these are helping magnetic fields, they are not opposite magnetic fields, hence the magnetic field will be reduced, so the inductance will also be reduced. Okay. Yes, keeping the other dimensions constant. Now before coming into some other types of inductors, basically the inductance quality factor depends upon the losses. Now there are two kinds of losses in an inductor. First of all, I already mentioned is that if you have a much larger area of the inductance, then it will, due to the magnetic fields to the substrate, eddy currents will be induced in the substrate. They flow in loops and hence they contribute to much substrate losses. Also another method is, Ashudebda mentioned, the skin effect. Now that severely affects the performance at higher frequencies, because the skin effect, as you already know, the skin depth is inversely proportional to square root of the frequency. So at higher frequencies the current effectively flows through a much lesser distance, less width, hence it contributes to severe losses. So part of the research in modern CMOS processes is to reduce this losses of the substrate by properly fabricating the metal layers. Even the metal layer at the top, it's not much distance from the substrate, because CMOS itself is not a very, it's not a very thick process. So it's around 10 microns thickness. Now that is enough to ruin your circuit in terms of substrate losses. Okay. Now suppose we have a huge number of turns. So people what they do is that they fabricate the inductor in two layers. So we get a few number of turns here and another number of turns here. Now the problem with this structure, can you guess the problem? What?
Resistance losses.
Yes, resistance one loss, so the quality factor will degrade. Another one? What about the capacitance? Yes, so within two layers we will have capacitance that will degrade the resonant frequency again. Now these inductors on chip in generally have a quality factor of 5 to 6, which is very low. So on chip QL is around 5 to 6 compared to around 30 for the capacitance. Now suppose in an application you need a very high quality inductance. So if the technology permits, we can use bond wire inductance. Now I hope you know what is a bond wire. In case you don't know, suppose we have a silicon die, on it we have circuit fabricated. Now you want to package the die. Now to package the die, to use it on a breadboard, you need pins, right? So you need to bring the contact point from on the die of the silicon down to the pin by using some bond wires. Okay, this contributes inductance. But the good thing about these inductance is that since this is not on silicon, this is not lossy. This has a very high quality factor. But the problem again is that you don't have much control over the actual value of the inductance. You can't just wind it up in turns. So this inductance is generally 1 nanohenry per millimeter of length. It's only dependent on the length. Suppose you need 2 nanohenry inductors, you will have to internally connect two pins and then use it total as the 2 nanohenry inductor. But as the slide shows, we have several losses also associated with the bond wire inductance if we just simply use it blindly, because we need to have a metal plate down to where the bond wire comes actually, and if we have subsequent metal layers, that will also contribute capacitances, extra capacitances. So this is just a circuit technique. If we can ground the bottom layer, see the equivalent circuit here. If we did not ground the bottom layer, the entire capacitance would have come into picture. However, if we just ground this point, we will have a much lesser losses or parasitics. So I already mentioned that high quality factor inductors can be fabricated by using the topmost metal layer, which is thick as seen in the diagram. So it will have less metal losses. However, this is seldom very sufficient to get a high Q. So people use additional techniques. Now the important aspect of the loss is, I already mentioned, the eddy current, that is due to the fields penetrating to the substrate. Now if we can somehow stop the fields by using a separate conductive plate. Now this plate is actually below the inductor in a separate metal layer and it's kept grounded. So that will have an easy termination for field lines, and hence the substrate losses will get tremendously reduced. However, if we just keep a planar shield, just a sheet of metal, then that will also have induced currents flowing through that. Hence we divide the strips in such a way that it does not hamper the current flow in this inductor. The primary technique is to divide it radially into wedges as shown. This is called a pattern ground shield. it's almost there in most RF CMOS processes. It's ready for the inductor. Okay. Another effect before coming into that is that loss mechanisms in the inductor is another effect is called the proximity effect. Now this occurs because you have, say, for a square inductor, you have two metal lines which conduct current flowing very close to each other. So one metal line will induce eddy currents in other metal line due to the magnetic field. See if the this direction is into the paper, so you will have electric field lines emanating from this when the current flows through this, and the magnetic field lines will go in a clockwise direction. Okay, so if we have side by side another conductor containing the same current, this magnetic field will induce eddy currents in this, the side by side conductor. Now that is called proximity effect. Now proximity effect of course can be reduced if we increase the separation between these two things, but that will again hamper the inductance value, as it will also hamper the capacitance value due to fringe capacitance. Now application of these inductors in modern CMOS processors is transformers. As you already know, we have 1:1 transformer or 1:2 transformer. Now this diagram particularly shows a 1:2 transformer, which is the middle conductor is the primary, and the secondary two inductors are shorted. This forms effectively doubles the number of turns of the secondary and achieves the 1:2 transformation. This is the second primary, and the bottom two are the secondary, and they are connected in between, only the two secondaries. And the lower one shows similarly a 1:4 transformer, whatever you can achieve. Now these transformers also have additional parasitics, because as I already mentioned, if you stack two metal layers, that will have capacitances, and also the coupling between these two will not be very high, because in the CMOS processors we use, the metal layer thickness is around 0.5 microns, and the separation between two metal layers is also around, say, 0.5 to 1 microns. So the coupling between these two layers, if current flows to these, if one inductor is fabricated here and one inductor is here, the coupling won't be that high. So what we can do is that we can interwind the two inductors on the same layer. Say, as seen in the slide, the primary and the secondary are both fabricated on the same layer. Hence, that will lead to a higher coupling, and the transformer will act more like an ideal transformer here. This is another way, another way of this implementation. This is a 1:1 transformer, because both the primary and the secondary have equal lengths of turns. Okay. Now before coming into microwave passives, say at lower RF frequencies, say less than 10 gigahertz, the wavelength. Now first of all, know that the free space wavelength will get reduced by a factor of the dielectric constant inside the chip. So the lambda g, the guide wavelength, will be inversely proportional to the square root of the effective dielectric constant. So say at 10 gigahertz, below 10 gigahertz, what people do is that, suppose you have a circuit here and you have a circuit here on chip on the same die, so you can connect simple by metal line at low frequencies, but at high frequencies we cannot use these lines, because the wavelength itself becomes, see, at 10 gigahertz the wavelength is very small, so it doesn't matter, very large, so it doesn't matter if that a line, the field distributions or the voltage distributions across the line will remain constant. So it doesn't matter, I mean, it does not act as a wave, but at high frequencies, since you can see a wave effect inside a normal transmission line. So from here comes the use of transmission lines instead of normal wires, microwave effects. Okay. Now the transmission line in general, you study two-port networks in your courses, right? So it can be modeled as a two-port network, and in general it's modeled like this particular block continues. It's a distributed model, not a lumped 20 meter model. Okay. So, and this is the input port and you have the output port on the other side. Now, this is called the LRCG model. Now, if you fabricate this type of transmission line on chip, see, this is the, suppose this is a line, so this is the signal path, but this is the signal path, you need to also have a return path because it's 2 port. So, suppose I fabricate another line below, that is the return path. So, then this can be used as a transmission line. Now, tell me what will be the capacitance and the losses due to in this case. Suppose this is one metal layer, say the topmost metal layer, and this is the signal path and this is the return path. Okay. Now, the capacitance will be simply the capacitance between these two. So, you know about C. The losses due to between these two layers will be G. The series loss due to currents flowing in this conductor will be R, and the inductance is always there. Okay. So, there are ways to quantify a transmission line. I think you have not read transmission lines except maybe electronics guys. So, one of the primary methods is I'll give a simple description of the characteristics. Suppose you have a transmission line which is pretty long, say infinite. Then the input impedance, it can be shown that it corresponds to a constant value which is the characteristic impedance, the simplest interpretation of the characteristic impedance. This is often what you find in normal oscilloscopes. The probes which you connect, they are marked as 50 ohms or 100 ohms. These are fixed. A line is characterized by its characteristic impedance. Okay. I'll come to that tomorrow. Maybe Asudevda will teach matching. Now then you will find that the use of Z0. Also another factor is the quality factor. Same case, the less the losses, the higher the quality factor. Okay. Now see that the Z0 coming from the previous this model LRCG model can be represented as square root of L by C. So yeah, that should be sufficient. Okay. Now there are different microwave structures available. I'll just, this is the microstrip line where this is the signal conductor, this the topmost metal layer, and there is a bottom ground layer which acts as the return path. Okay, and in between there is the dielectric. Suppose these are two metal layers M6 and M5. Now what suppose we fabricate the microstrip inside the chip, and this is the cross sectional view. So this is the current flows into this and comes out of this, the signal line, the WS, and this is the ground line. Let's take it as infinite for the time being. And also we have the substrate height H. Okay. Now it can be shown that it's almost intuitive that the characteristic impedance will only depend on WS by H, because these are the only two parameters you can play with, right? Also see that in CMOS processes you don't have much control over H, because the metal layers are already fixed at equal distances or individual distances from the substrate. You cannot simply play with the H, which is the silicon dioxide or the dielectric you are using between metal layers. Okay. So the only parameter left to play with to control Z0 is WS. Now suppose you need say a high Z0. Okay. So what will you need according to this expression? Yes. So you will need a low value of capacitance. That will mean WS is low. Okay. That will mean more metal losses, and that will mean less quality factor, because the current actually flows through a much less width of the conductor. So microstrip line is in general not used for CMOS processes or in RF processes. Also another issue of concern is that if you have side by side another microstrip line, okay, so the electric field lines, say it terminates to the ground, always electric field lines. So we can have terminations from here if the current flows in this direction. We can have terminations from here, and in between we can also have terminations. Okay. Also we can have coupling between these two lines. Now that is a major issue in case of high frequencies, that coupling becomes an issue of crosstalk. We don't want that. So the best way to use these microstrip lines in CMOS is by shielding them with additional ground layers in between. So the simplified structure will be simply the middle center conductor. We have additional grounded lines, grounded plates. This is the cross sectional view below that. So we don't have the issue of crosstalk here. Also, there are 3 parameters to play with. So first the WS, this is the WG, the ground line width. You can also play with that. It won't affect much, but still. Then is the S, the separation, which has a tremendous impact on the quality on the characteristic impedance. See that? Okay, I'll come to that later. See, and also you have the H, as in the microstrip. Now suppose this is the signal path and this is the return path. Now suppose I increase S. Now what will happen to the characteristic impedance? See that you are separating two signal conductors which conduct current in the opposite directions. So the effective magnetic field in between will increase. So inductance will increase and hence the characteristic impedance will increase. So you can get all ranges of characteristic impedance with this structure, which is called as coplanar waveguide. These all structures are called waveguides. They basically guide the wave rather than, just a simple wire. Okay. Another method, you can add additional degree of freedom to the characteristic impedance by just connecting a ground line below. That will enable you to add additional capacitance to the line and hence also change the characteristic impedance by much. But the problem with this structure is that, see, what will be the electric field lines here? Electric field lines from signal to ground, partly through the air, okay, partly through the dielectric, and partly below to the ground line. Now since this shield is grounded, these are also grounded by the way, so we'll have more electric field lines crowding inside the dielectric rather than the air. Now since the dielectric is always more lossy than the air, we'll have more losses here and the quality factor of this structure will degrade. Okay. So in general, these two types of microstrips and coplanar waveguides are used in high frequency CMOS devices to connect between 2 points. There are several applications of this structure also. I'll be not able to come into that here itself. Now another important block of the design is the antenna design. Now it is very difficult to fabricate the antenna on the same substrate, okay, because simply a simple wire which conducts the current can act as an antenna, provided most of the electric fields flow out into the air, not into the substrate. But since you always have a return path below, most of the field lines will crowd below. It will not go up into the air. So what people do is that they fabricate the antenna on a different substrate and control the structure in such a way that you have more electric field lines penetrating, less electric field lines penetrating into the substrate. It acts as a radiator mainly into the air. So these types of antennas in general are not fabricated on silicon due to the higher dielectric constant of this material, and hence generally antennas are on a separate substrate, but it's on the same total package. So this is basically the summary of whatever microwave devices you will be using. You can have a brief overview if you anyways you will be studying, most of the electronics guys will be studying in your future classes. But it's good to know that when you design chips, at high frequencies you should be able to identify these effects, as not use very thick lines that will contribute to higher capacitance, and hence my losses will increase, the speed will decrease. That's it. Any questions on this? All right.